Hey guys, so here we go for lesson 3. Um, okay, so we've looked at position and time graphs, we've looked at velocity time graphs. Again, all of this should be review. I'm hoping it's bringing back memories. For some of you, Physics 11 was a long time ago. Here we go, we're on acceleration, conceptually and as a graph. So acceleration is the rate of velocity change per second. In this section, we're looking at the constant acceleration. We won't look at anything other than a constant acceleration in Physics 12. This means that the velocity change per second is constant. Units of acceleration are meters per second squared. So for example, what does an acceleration of plus 1.25 I hat meters per second squared mean? Well, let's talk about it. I've got some times here. At t equals 0, t equals 1, t equals 2, and t equals 3 at these different times. If it starts at rest, that means my initial velocity is 0. One second later, if I'm giving this object a positive acceleration of 1.25 meters per second squared I hat, after 1 second, our object's going to be moving at 1.25 meters per second in the I hat direction. A second later, it's going to go another 1.25 meters per second, which is going to give us 2.5 meters per second squared in the I hat direction. And at t3, well, it's going to be at 3.75 meters per second squared I hat. The acceleration is constant, it's positive. And so every second we move in time, our velocity is going to increase by a speed of 1.25 meters per second. Relatively straightforward, I would think. Let's take a look at B, and then I'm going to give you an option C down here, so don't take up too much space. B, the object is moving initially east at 2 meters per second. So I've got t equals 0, t equals 1, and t equals 2. At t equals 0, if I've got a velocity, I'll just draw this all in here. Velocity equals. Initially, it's moving east at 2 meters per second. That's positive 2 meters per second I hat. And I'm going to accelerate it by a positive 1.25 meters per second squared I hat. So it's already moving positively. The acceleration is positive, so it's going to be increasing in speed. This thing is going to be now moving at 3.25 meters per second, positive I hat direction. I hat is just positive vector. V at 2 seconds is going to be, again, you take your velocity and you add to it the acceleration. It's going to be 4.5 meters per second. It's still going to be positive. It's still going to be in the I hat direction. Relatively straightforward. What, though, happens if I have an initial velocity of negative 4 meters per second I hat with this same acceleration? What's that going to do? So we're going to have t equals 0, t equals 1, t equals 2. And I'm going to go over here, t equals 3, and t equals 4. What happens here? I'm going to draw all this out. So I've got v at these different times. So time t equals 0 with an initial velocity of 4 meters per second. I've got negative 4 meters per second I hat. And I have a positive acceleration. So my velocity is going to start to get more positive. If it starts at negative 4 meters per second I hat, and I'm adding to it positive 1.25 meters per second, what the acceleration means. Now I'm going to be increasing my velocity up from negative 4 to negative 2.75 meters per second in the I hat direction. So it was traveling negative and it's slowing down, is effectively what that means here. If I have a negatively traveling object and a positive acceleration, it has to slow it down and then speed it up in a positive direction. So negative 2.75 plus 1.25 is going to give me a V of 1.5. It's still going to be negative meters per second. I hat at T3. 1.25 means I'm now at negative 0.25 meters per second I hat. And at t equals 4, my velocity is now going to become positive. So it's going to have a velocity of 1, positive 1 meter per second I hat. Every second, I added to it 1.25 meters per second of velocity. And it was at negative 4, then negative 2.75. So you can think of it here. If it was big N negative and it's becoming less negative, the object is slowing down. So what happened between T3 and T4? Well, at some point in here, the object had to stop and switch direction, is what happened in here. Somewhere in here, the object stopped and turned. I don't know how it was for you guys in grade 11, but typically acceleration is difficult to visualize and interpret what it actually means. It's not, we can draw it in there. It's a vector. It has a magnitude and a direction. But typically it can be tricky to deal with. Because it depends, well, yeah, because the acceleration depends on, or what the acceleration is doing, depends on what the object was doing already. So you need to consider its velocity until, you need to consider its velocity to be able to interpret what the acceleration is actually doing. So if the acceleration of an object is towards the east, does that mean the object is moving towards the east? Pause the video, think about this for yourself. 3, 2, 1, okay. No. The acceleration of an object has no bearing on the direction that it's moving already. Okay? If v is this way, and the acceleration is this way, this means the object is speeding up. But you could have it that the velocity is this way and the acceleration is this way. And what that means is you have an object, this block is moving, the motion is that way. The acceleration is that way. So the object is slowing down. Okay. Stuff you should have dealt with last year. Okay. The difficulty in visualizing acceleration, as I've said already, is that we tend to confuse it with velocity. The direction an object is moving and the rate at which it is moving are both related to velocity, not the acceleration. To determine the direction of the acceleration, we need to watch the object for a period of time to see how its velocity is changing. I said that a little differently before, but it amounts to the same thing. What the acceleration is actually doing to an object depends on how the object is already moving at the start of the problem. So there's 4 scenarios here. So I'm just going to draw 4 little boxes in here. Scenario 1, my velocity and my acceleration are in the same direction, both to the right. You have an object that's speeding up. If you have an object in this direction, if both my velocity and acceleration are this way, again, it's speeding up. It's just going, the speed is increasing in a negative direction. So in this case, the velocity would be getting more and more negative. If I have a velocity that looks like this, and my acceleration is this way, if it's accelerating to the left, but it's moving to the right, well, what does that mean? It means it's slowing down, moving right. And conversely, if I have a velocity this way and an acceleration this way, in this one, it's slowing down and moving left. If you give things enough time, though, this guy will eventually become this. If my acceleration stays the same, this will eventually become this. As it slows down, if my acceleration remains constant, slow, 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 as v gets to 0, and then v is going to start to pick up this way. This situation will become this situation here. And conversely, this guy is going to become this guy given enough time. Okay, so I want to draw a diagram and state the direction of the velocity, i.e. positive or negative I hat or j hat. We've talked about i's and j's. I hat is the x direction, just review. And j hat is the y direction. Positive is typically to the right. Negative is typically to the left. Or for this one, positive would be up and negative would be down. We've got an object moving west and slowing down. So if it's moving west and slowing down, I got that. Velocity has to be that direction. And if it's slowing down, the acceleration has to be the opposite direction. If the object is falling and slowing, you know what? Here, I want you to pause the video. And I want you to try and draw these for yourself. And then when you unpause it, I'll go through them for you. So pause the video, draw those scenarios. Okay, assuming that you did that, let's draw these in. If an object is falling and slowing down, it means it has a velocity downwards and an acceleration upwards. If it's moving east and speeding up, speed is increasing, so that means velocity and acceleration have to be in the same direction. If it's moving up and slowing down, that means if it's moving up, my velocity must be up. If it's slowing down, my acceleration must be in the opposite direction. And then in E here, we've got a couple things happening. We've got an object moving up, slowing down, stopping, and then beginning to fall, speeding up. So we're going to break it up into 3. So first, I've got an object moving up, slowing down. So my acceleration, it's moving up, so my velocity is up, slowing down, which means my acceleration is down. Stopping, the acceleration doesn't change. The acceleration is still down. It doesn't stop accelerating, but it has no upward velocity. For a moment in time, it stops. It's still accelerating downwards, but now it's starting to speed up in that direction. Flip the page. We can do numerical examples to help us figure this out as well. We're going to fill in this chart here, and then we're going to draw some graphs. This lesson should also be pretty, this lesson also pretty short. So I want to fill in the chart for a positive 1.25 I hat meter per second squared acceleration with an initial velocity of 0, 2, and 2 east and 2 west. So we've already kind of done these. So at least the first 2 we've done. So it's going to be 0, 1.25, 2.5, and 3.75. These were numbers from the first example we did. And this one's going to be plus 2, plus 3.25, plus 4.5, and plus 5.75. These are all meters per second because they're velocities. This one we didn't do. I gave you a different value for the third one, so let's actually make sure we do this one properly. 2 meters per second west is negative 2 meters per second in the I hat direction. At 1 second, if I'm increasing the velocity by 1.25 meters per second, that's going to give us a new velocity of negative 0.75 meters per second. Adding 1.25 again is going to give us 0.5, and then adding 1.25 again is going to give us 1.75. meters per second in meters per second. And I'm just going to write up here again. I should have done this to start, just to remind us. Clearly, the acceleration for each one of these is that. Now we're going to produce growth. So we can see what's happening here. Like you're not moving and it's starting to accelerate in the positive direction. The velocity is going to increase in that direction. Same thing here. If you're already moving in the positive I hat direction and my acceleration is in the positive I hat direction, it's going to just keep moving faster. This one, if it's moving in the negative I hat direction and the acceleration is in the positive, it has to slow down first and then begin to speed up in the other direction. So let's see what that looks like here. We're going to produce some graphs. Now, it's important to remember, let's make a note. Well, let's not. Let's make the note after. Based on the data that we've collected, we're going to make some graphs. So for graph A, here's A, here's B, and here's C. We were at 0 and 0. At 1 second, 2, 3, 1 second, we were at 1.25 and 2.5, and then 3.75. So here we are there, and here we are there. Interesting. For the second one, we started at 2. 1, 2, 3. Here we are at 2. And then 3.25, 4.5, 5.75. There we go. And then the last one, we're starting down here at -2. 1 second, 2 seconds, 3 seconds. -2, -0.75, 0.5, 1.75, So what's happening here? Up until that point right here, we've got an object with a negative velocity, but if we look at what the slope is here, the slope on all three of these, slope on a VT graph is the acceleration, and constant acceleration looks like a straight line. For those of you who are also in calculus, as soon as you start doing derivatives, this will make sense because acceleration is the derivative of velocity. So let's take a look at what's happening in this case here, C. At this point, I've got a constant positive acceleration for a negative velocity. So here it's slowing down. Right here, at that line, this object has stopped. And over here in this section, you've got an object that's speeding up. We could also make, and we're going to, position time graphs underneath this thing. We don't know anything about the initial position, so I'm just going to assume the initial positions at the origin for each one of these. Let's take a look at what's happening here. I've got an accelerating object. So the velocity is not constant. A constant velocity would be a straight line. But I've got a constant acceleration now, which means my velocity is increasing. So So on a position time graph, that's what acceleration is going to look like. A constant acceleration is going to look like a curved line like this. Same thing with this guy here. We don't know anything about the initial position, but we do know that he had an initial velocity already, but he's still accelerating. So the curve is actually going to look exactly the same. All we know is that we've got an accelerating object starting at the origin. What's happening with this guy? For this guy, he has a velocity. It's in the negative direction. It's down here. I continue this line down. So for this first section, our object has a negative velocity and it's accelerating or it's slowing down. What that's going to look like is actually it's going to look like this. You can see my velocity is negative and it's getting shallower and shallower and shallower. For here, all of a second, my velocity is going to be 0. And then we've got an object that starts to speed up. So again, we've got acceleration happening in a positive direction, so it's going to curve up like that. For those of you who are also taking calculus, this is going to look real familiar here, coming up pretty quick here. You should be starting with limits, and then you'll get into this pretty quick. At this time, right here, our object has stopped. If you've got questions about any part of this, I'm happy to explain more of that. This is more of me trying to make a connection with, or for those students who are also studying calculus. So if you're not studying calculus, don't worry. This will make sense one day when you do. So I'll do another one of these. We've got the same idea. If I've got the motion, we want to describe the motion depicted on this position graph and then fill in the missing graphs. So here's what's going on. I've got a straight line, a curved line, and a straight line here. A velocity graph and an acceleration graph. So I have 3 zones. I got zone 1, I got zone 2, and I got zone 3. Here, we know that's a straight line, and this is a straight line. So we have constant, we know. Let's write out some stuff that we know. We know that in 1 and 3, we've got a constant velocity. And we know in step 2, the object is accelerating from V1 to V3, the velocity in chunk 1 to the velocity in chunk 3. Because V1 is greater than V3, V1 is less than V3, means my acceleration has to be positive because it's accelerating from a smaller speed to a bigger speed. And we know that because this line is shallower than that line. So let's do this. Constant velocity for chunk 1 looks like that. And 3 is bigger. So there we go. It's constant velocity, so it's flat lines on a velocity graph. And we know that the acceleration is positive, and we were told that we were to assume that it's constant. So a constant acceleration on a VT graph is going to be a straight line, connecting our 2 previous velocities. And then the acceleration graph, it's not accelerating, so it's going to be down here at 0. It's not accelerating this third chunk, so it's going to be down here at 0. But it does accelerate, and it's constant for this bit here. We're going to have some flat-lined acceleration right there. So let's consider what's happening down here. We're going to describe the motion, talk about the greatest positive value, or velocity having the greatest positive value, acceleration having the greatest positive value, and at what time does the position have the greatest value, positive value. So what's happening here? We've got an object, and the object is moving in a, so the velocity here is positive. So it's moving positively. In this first chunk here. I'll call this 1, 2, and then I'm going to call this guy down here 3. Break it there. I'll break it there. So it's moving positively. And it's accelerating. We know that because it has a slope. And the slope is positive. it's moving positively and accelerating positively, so this thing is speeding up. And in 2, the velocity is still positive because we're above the x-axis here, so we're still moving positively, but the slope is now negative, which means our acceleration is negative. Accelerating negative, so this thing is slowing down. Actually, we're going to call this 4 right here, and I'm going to call this line 3. At 3, the object has 0 velocity, so the object stops. And then at 4, which I'm just going to put right there, we have the object, the velocity is negative, so it's moving negatively. It's accelerating negative because the slope is negative, which means this thing is speeding up. Which means it's heading back in the direction it came from. So let's talk about this here. At what time does the velocity have the greatest positive value? Well, the velocity has the greatest positive value at the moment it's done accelerating positively. So right here, it's at 3 seconds. So that is the time the object has the velocity is the greatest positive value. The position has the greatest positive value here at at step 3, which is t equals 5 seconds. Because this entire time it was moving positively. Oh, no, I screwed that up. That should be my answer for D. The acceleration has the greatest positive value. Well, acceleration is constant for this chunk and it's constant for this chunk. It's positive and big from 1 to 3. It's constant and positive that whole time. Has the greatest positive value in this window. There it is. So now I'm going to give you some homework. More homework for today. I want you to take a look at these. There are 9 questions. I want you to do all of them. And I'm not going to post a 3rd video today. This will be everything. I'll post some more tomorrow. As always, if you have questions, feel free to email me or come see me at lunch before you leave.